Okay, we're going to get started. This room is sponsored by Rubicon. Rubicon Project has engineered the Advertising Automation Cloud, one of the largest real-time cloud and big data computing systems. The company's mission is to automate the buying and selling of advertising by offering innovative products to connect buyers and sellers globally. For more information, visit rubiconproject.com. We ask if you would take a moment and fill out a speaker survey. It's on the card that came with your badge. There's a barcode to scan or a URL. Okay, our next talk is on NATS, a nervous system for distributed cloud platforms. Our speaker is Derek Collison. NATS is an always-on, high-performance, lightweight, and resilient messaging system to architect sophisticated control planes needed for next-generation cloud-based systems. And without further ado, I give you Derek.
So let's see. Okay, it's on. Thank you. This is actually probably twice as many people as I thought I would get for a now CEO talking about a low-level messaging system. Here's some info about me, where you can find stuff about what I've done and not, especially on the GitHub repo. But, you know, why should you even listen to me? Whoop. I need to actually... There we go. That's better. That's the information. And then, why should you even listen to me? And the answer is you probably shouldn't. All right. Most of the company that I work at now, they want me to keep away from the keyboard as much as possible. But in a prior life, I spent about 6 years at Google. Prior to that, I spent about 12 years or so at a company called TIBCO, which just got privately sold and most people don't know about, but in the late 80s and early 90s, it kind of revolutionized the way Wall Street works. And a lot of the technologies that I built there in terms of Rendezvous and EMS still run in Wall Street. So trade distribution, quote distribution, back-end trading, and settling and stuff is still running mostly on Rendezvous and EMS. Matter of fact, we were at a customer the other day and they still have 600 EMS servers, which is kind of interesting. I also architected Cloud Foundry when I was at VMware before it moved to Pivotal. And essentially I've been building messaging systems and solutions for over 20 years. So I usually get it right. Not always, but I usually get it right. So why messaging? A little bit of background. I'm sure if you've had any talk around Docker, you've also heard microservices, right? Microservices architectures. And it's essentially the notion that software systems are being decomposed into smaller and smaller parts. And that trend is going to continue, right? So that you have very purposely built small pieces of code that can be lifecycle managed independently. They have to figure out how to talk and coordinate amongst everybody else. What's interesting is that when I was at Google, from 03 to 09, we had a massive explosion of the number of things that were answering basic Google query. So in 1999, a Google query touched about 12 computers. In 2009, I think it was about 10 to 11,000 computers. And I would guess right now you're getting close to 100,000 computers. So when you search for the Oscars on Google, you know, and hit enter, you're actually touching a massive amount of machines. And how those machines actually coordinate, talk to each other, is usually based on some level of communication protocol. Event-driven architectures, which is I'm a big fan of. And HTTP, which I actually love. As an interface, though, it only goes so far, right? It's usually point-to-point. It's good for moving large pieces of data around. There's also the notion of one-to-N and one-of-N patterns, meaning I want to talk to a whole bunch of people, or I want to talk to one person, but I don't know which person that is. And it might be a whole large N of them. We're going to talk about that a little bit more. Cascading request and reply, the notion that I want to create a request, and it might ping-pong between 5 or 6 different elements before I actually get the answer back. And then subject or topic-based routing. So a different level of routing protocols versus IP and a port. So this is fun stuff. Again, I think people call me experienced now, not old. But in terms of a network recap, we have IP, we have TCP and UDP, right? So we have this notion of streaming versus limited packet size and unreliability with UDP. The first version of Rendezvous actually used UDP, and I built the current generation of what was called the TRDP, which is the Technicron Reliable Datagram Protocol. And what we were trying to do there is effective one-to-N. All right, so we want to be able to say effectively, I want to send it out to 100 people, and I don't want to have to send it 100 times. And at the time, that made the most sense. When we were doing this code, believe it or not, multicast didn't even exist. Now, multicast obviously came on board, and we were actually involved in that. I don't know, does anyone even know multicast? Yes? Anyone use multicast? Interesting. That's surprising. When we were doing all this work at TIPCO, Technicron/TIPCO, what was interesting is that we had access to a lot of the network elements, and we could actually see what was going on inside of there in terms of the kernels that ran inside of those. In the late 90s, right, with the explosion of the internet, the World Wide Web, something very interesting happened. Inside of a network element, there's a fast path and there's a slow path. And what happened was is that TCP was the only, child, so to speak, in the fast path anymore. UDP, broadcast, UDP, point-to-point, multicast, all was outside of it. And that was kind of a response to the internet, right? Everything was TCP, IP, HTTP, of course, on top of that. My opinion, multicast essentially failed, right? The administration of it was problematic. It became difficult to use. Matter of fact, my understanding, and I don't know this for sure, but I understand a lot of Rendezvous customers have actually gone back to the reliable UDP protocols and not multicast. Multicast, for the most part, is either trunked or totally disallowed in any type of cloud platform. And UDP in most cloud platforms is trunked, if it's even allowed at all, at the top of the rack switch. So you can't actually use it to kind of do anything. And what's interesting is that for certain types of N, probably, depending on your message size, 30 or so or less, it actually is faster to send it 30 times from one point, which is kind of non-intuitive. So in terms of messaging, this will probably be a recap and everyone's going to laugh at it, but I just want to make sure we're all level set. There's basic messaging patterns around publish, subscribe, queuing, and request reply. Publish subscribe is you send it to a topic or a subject, and anyone who's interested in it can actually see it. We're going to do kind of a live demo in a little while with NATS, and you guys can kind of see what that means. But the cool part about why it was actually put together was very, very interesting, and I'll talk about that in a second. Queuing is a general mechanism by which you have N receivers, but every message only goes to one of them. Right? This is not rocket science. It's not really exciting or sexy. But there's very, very interesting, distinct differences between what I mean by distributed queuing and what a lot of people think queuing should be. Request reply is I ask a question, I get an answer. And if you're only asking one person, right, you can just use TCP, right, with some stuff on top of it. If you're asking a whole bunch of people, let's say they're forming queue groups and you're getting one, response, a lot of messaging platforms do that as well. What's interesting, and it's a pattern that I use all the time, and it's one of the things that I built into NATS on day one, which we'll talk about, is what happens if you're asking a question, and I'm actually going to ask every single person in the audience, and all I want is the best and first answer that I can get. There's massive ramifications on messaging systems, infrastructure, and the client libraries when you do that. I'll give you an example of why you would want to do that. Google search is really fast. And the basic premise of why it's fast is that they divvy up the corpus of the web, right, into shards, and then each shard is replicated. So each time you hit something in Google, each shard, it's actually sending it to every single one of you, and the fastest one back it uses, and it wants to throw away all the other ones. From what I remember, it could be different now. Inside of Google, it would just chop the connections after it got the first answer. But if you take a typical messaging library, right, a JMS type of thing or a RabbitMQ or something like that, and you go, I'm going to ask a question. I have no clue how many people are out there, and I want the answer. If you look at the CPU load of your client library that's doing the request, you're going to see massive spikes all day long. All right? And they're linearly appropriated to how many responders are out there in the network, which you shouldn't care about. I shouldn't care if there's 1 of you, 10 of you, 10,000 of you. So we'll talk a little bit more about, a priori pruning of an interest graph, which is what NATS can do. So some of the use cases, and again, I've been building solutions on top of messaging systems for quite a long time, but this kind of captures what we actually do with them, right? Addressing and discovery. A really funny sidebar that everyone will kind of get a kick out of is that I was very fortunate in the early 90s to actually talk to Steve Jobs directly when he was at Next. And he wanted to embed TIBCO's Rendezvous into the Next Step boxes. And the CEO of TIBCO said, I want you to do this, and don't talk tech to him, right? Don't talk about pub, sub, and all this other stuff. So I kind of remember saying something like, well, Steve, it's a way to have location transparency, discover, and utilize services in any platform. He said, great, I'll pay you $1 million lifetime. And I said, no, we can't do that. And he said, you waste my time, and he walked out. So that was my 5-10 minutes with Steve Jobs. Why it's an interesting story is that when Steve went back to Apple, they created a protocol called Rendezvous. And its description was location transparency, where you can transparently find and discover services. And I said, hey, that's not right. He said, I don't care. And he was probably right, but they did change it to Bonjour. So that's what the Bonjour service is. You can do command and control, a control plane, and that's what we use it for a lot in our system. So Cloud Foundry used it as a control plane. And Apcera, the company I'm with now, we use it as a secure control plane as well. But it can do load balancing, end-way scalability, location transparency, as we talked about, and fault tolerance. So why pub sub? So Vivek Ranadive actually described this to me when we were starting to build the first version of Rendezvous. He said, it's a radio versus a phone call. And the reason that Wall Street cared about this was, if I actually give you the quote of IBM, and then I keep walking along, right, and giving everybody the quote of IBM, by the time I get to him, your version of the world is old. And we were all starting to see this notion of programmatic trading, which meant that you had a fair advantage over him, right, because I could give it to you first. And so the notion was, how do we actually do quote distribution where it's fair, right? And one of the first reasons that we actually went down publish, subscribe, and reliable UDP was to make it fair. There's actually massive embargoes and stuff in terms of fairness. Obviously they can't change the speed of light, but that was kind of one of the original reasons it actually existed. One of my big things is I always say, don't assume the audience. When you send a message, don't assume who's going to actually be watching it or looking at it, right? And I've seen it time and time again where, of course, when you're building the first part of the system, you're like, I'm sending a request and I need you to respond to it. But later on, it's like, well, hey, what if we want to measure something? What if we want to log this thing? What if we actually want to do X, Y, and Z? And a lot of messaging systems kind of go, oops, you can't do that, especially if you do what's called publish-based queuing, which we'll talk about in a second. So queuing. Now, this is the interesting part. And again, this is kind of geeking out, and I might lose some people, but it's really important to me. Is it a publish or is it a subscribe operation? Now, most people in the audience probably understand queuing as a publish operation. It's kind of like you get into the line at McDonald's and then everybody kind of goes to the right first line. And that's comp sci theory. And that's when you sending a message, you stick it physically into a queue and then people are pulling off of the queue. A subscribe operation is very different, right? Subscribe is what I call distributed queuing, and essentially it only takes that part of, one member of the queue group is going to respond to any given message. It's subtle, but it's actually extremely important, at least, again, to me. So request reply. Again, don't assume the audience. That's what we talked about with the Google example. I don't know how many people I'm asking, the question of. How many responders? I shouldn't care. The system should actually auto-adjust everything around that. And for me, it's always built on publish, subscribe. So the way NATS actually does request reply is it creates an ephemeral, unique subject. It subscribes to it. It sends the message out with that as a reply, and then when you reply, I'm the only one kind of listening to it. But if someone comes into the system and says, I want to see all the traffic in the system, right? We have wildcards and subjects and topics. They can, and they'll see not only the request, but the response. A lot of systems, you see the request, you can't see the response whatsoever. So these are some of the enterprise messaging patterns. You've got persistent, store and forward, distributed transactions, that was a really gnarly one, and then enhanced delivery models. And what I mean by delivery models is at most once, at least once, and exactly once. Anyone have heard of those delivery models? Does that ring a bell at all? Okay. What NATS does is it most wants. It's a fire and forget type of system. I actually designed and built an exactly one system for several financial clients, and they're very, very hard if you're going to do it correctly. So the first time we delivered this system to the client, they're like, okay, great. They go to spin it up, and the system gets halfway spun up, and it sees a printout saying system not supported, and it shut down. And they go, what the heck? You know, what are you doing? And I said, do you realize that for exactly one semantics, I have to have transactional semantics on my own, and if I can't tell if your hard drive has cache enabled and doesn't have a capacitor big enough to spin the the bits into the disk, SSDs didn't exist back then, that I can't support you. And they're like, well, what do you mean? You know, we actually eventually went with a NetApp with 16 gig, which was massive at the time, of NVRAM and all this other stuff. It's actually not needed, in my opinion. Exactly once is a problem that doesn't really need a solution. Right? There's other ways to do it, in my opinion. So what if we looked at the problem differently? You know, should messaging systems do everything under the sun? Store and forward, persistent storage, distributed transactions, you know, multiple delivery models. And I've built those systems. You know, EMS has every single thing we just listed. And I think it's, you know, it's still a closed source per pay product from TIBCO, but my understanding is it's one of the largest revenue generators still to this day. And it was, you know, done right with myself and an amazing team there. But when I was looking at what I thought modern distributed platforms would need going forward, I didn't find myself saying distributed transactions, persistence, you know, exactly once semantics. So should it just do much, much less? You know, and a lot of people will knee-jerk and say, well, wait a minute, I want it to store it and make sure that it gets delivered and all this other stuff. And the first thing I ask is, I say, who really cares if it gets delivered? It's a hard question to go about, but if you start thinking about use cases, right, your messaging server could blow up. So what happens when it blows up? What do you do? Why can't you do that in the endpoint necessarily? Now, there is a notion of I'm going to queue something up and later on we'll do batch processing. And I believe that type of store and forward model and pattern works. But a lot of times it's almost an anti-pattern to expect that once I give it to the messaging system, it's going to take care of everything, because it simply won't. So much for the background. So NATS, you know, .io. So the inspiration. Now this is corny, and I admit it's corny, but it means a lot to me, which is I started looking at, you know, these distributed systems becoming larger and larger and more moving pieces and trying to figure out how they're coordinating. I'm like, well, you know, again, it's corny. You know, how does the brain do it? Well, the brain doesn't store and forward. It doesn't do distributed transactions. It doesn't do, you know, exactly once semantics. It's a fire and forget model. It really is. The neurons in your brain are firing, and they fire once, and they, you know, spray and pray, right? They hope. So for me, that inspiration started to drive what we actually designed in terms of NATS. And so, not like Brendan, but I try to be as close as I can on a regular basis. I love high performance. I spent a tremendous amount of time in the TIBCO days squeezing every ounce I possibly could out of Rendezvous and EMS. And NATS is a similar way. It's just I'm older, I didn't have enough time, and I don't like writing in C anymore, although it's still my favorite language. I just can't do it. It's always on and available. It's kind of like a dial tone. And that's very different, because if you look at enterprise messaging systems, they are actually predicated on the fact that they're going to try to do everything possible for the client when the client asks them to do something really, really weird. Meaning that they'll actually take everybody offline because they're trying to do this thing. The queue's getting, you know, it's 1 million messages, and we're running out of disk space, and we're in swap hell, and we're doing this. NATS doesn't do that at all. NATS version of the world is I protect myself at all costs, and I always have to be available. Extremely lightweight. You know, if you need 450 dependencies to apt-get install to run your Erlang VM, and it's coming up and it takes up 200 meg when you first boot it up, that's not going to work. We talked about it. It's fire and forget. You know what I mean? At most once. It's fundamentally built on pub/sub, and that's it. Now there's notions of queuing and request reply that we'll talk about, but underneath the covers, it is a pub/sub engine with an extremely high-performance routing mechanism to actually route between subjects and be very intelligent around cluster semantics. It does have distributed queuing. So, if all of us were responders and we all said, we're going to listen to foo, and then a couple of us said, we're going to listen to foo, and we're going to join a group called bar, the publisher would send the message once, and the system is actually saying, okay, everybody in the bar group, one person gets it. Everybody else who's direct, pub sub, they all get it. There's another group in the background that they're called the Baz group. One of them gets it. And you can scale this as much as you want. And again, don't assume what the purpose of the message is. And again, the request reply. But my version of a request reply is, yes, it's a traditional one. I'm going to ask one person, I want one answer. But moreover, the pattern that we use a lot, and I've used it in distributed scheduling algorithms that actually people can actually see, is I want to ask everybody, and I want to get the very first best answer. And it's a pattern, again, I use over and over again. It's a pattern that Google uses to make Google search fast. And ours, both in the original Cloud Foundry and then Apcera's Continuum platform, we use it for our distributed scheduling algorithm. So I literally say, hey, I got this thing to run. I'm going to ask everybody. And what's really interesting is that the first person back wins. And the beauty of an algorithm like this, to make it drop dead simple, is that everybody does two things in the audience. They decide whether or not they can or can't run it. And if they can't, they just ignore it. If they can run it, they actually determine how long they're going to wait before they respond, based on things like memory pressure, where they're already running that job, right? So there's a repelling factor. And it's drop dead dumb. Yet it looks extremely intelligent when you actually visualize it at scale in terms of how things are actually moving around. And so we wanted to make sure that NATS was actually highly tuned for that, right? You didn't have these massive CPU spikes. So what is it not? It's not an enterprise messaging system. Doesn't have persistence. Doesn't have transactions. Doesn't have any enhanced delivery models. And it's really not a queuing product per se. It's not a store and forward mechanism, right? It does have queuing delivery semantics of one of a group, but it doesn't have this notion of put something here, hold on to it, and then make sure someone actually consumes it. It's trivial to build that functionality on top of it, but NATS as a core level nervous system does not do that. So it's kind of interesting to me that I'm even here. When I built it, everyone kind of looked at it and said, well, are you going to popularize this thing? I said, trust me, nobody will want to use this except me. I built it strictly for myself to originally power Cloud Foundry. That was it. Now what's interesting is that as mind shifts and cultures have changed, you're starting to see people wanting to build distributed cloud platforms or distributed systems without using traditional enterprise heavyweight messaging systems. Some are just using HTTP, some are using some of the protobus stuff out of Google, some use Rabbit, although Rabbit's kind of still heavy in kind of an enterprise messaging type system. But I really did build it for myself, so it doesn't hurt my feelings if you say you don't want to use it at all. Now, what's unique about it? It's a clustered mode server. Anyone know full mesh one hop versus directed acyclic graph semantics? No. EMS, which was built at Rendezvous, actually supported both modes. Directed acyclic graph, you can kind of just hop, but you can't make a cycle. Full mesh one hop is if you have two, they're talking to each other. If you have three, they're all talking to each other. NATS is a full mesh one hop clustering mechanism. The clients are cluster aware. Irregardless of support from DNS or IP load balancing or anything, you can literally give a client a pool of servers, say here you go, and then it will actually randomly figure out which one to connect to. If that one dies, it automatically reconnects instantaneously to the next one. We've got a decent amount of clients: Go, Node.js, Java, SCaLE, Python, Ruby. We're going to be adding a couple there in the futures. It does the auto-pruning of the interest graph, and we'll talk a little bit more about that in a second. It's always pub sub. It makes no assumptions. It does do distributed queuing across clusters, which early in the days of EMS I couldn't figure out how to do. They figured out how to do it, and I think I do it in a different way. But the mechanism of the first release of EMS was you had to know where your queue group was, which server it was attached to, and you'd have to attach to that server. In NATS, you can attach to any server you want, and we could have 1,000 servers, everyone is attached to a different one, and you guys could all be part of the bar group, and it just works. And it's a text-based protocol. Everything I've designed in my career was always high performance bin packing, all this other stuff, you know, figuring out little Indian versus big Indian, and, you know, byte and word boundaries and all kinds of just stuff that'll put you to sleep. A good friend of mine created a system called Redis, and Redis is actually text-based, and him and I were talking about it. And I said, computers are so fast, I don't think text-based matters anymore. And that's actually the truth. It doesn't matter anymore. So performance, again, not as good as Brendan, but I try, you know, at least as best I can these days. NATS was originally written to support Cloud Foundry. It's still in use by Cloud Foundry, HTC, Baidu, and some others. It was written in a weekend. So the first version just had a Ruby server and a Ruby client, because Cloud Foundry originally was written in all Ruby. But the first version could do 150,000 messages a second. Compare and contrast that to maybe like a RabbitMQ, which probably does about 9,000, maybe 10,000 a second. We rewrote both the client and the server in Go. So Go is the language that is the dominant language within Apsara. It's a language out of Google. If you haven't checked it out, I would definitely highly recommend it. And the first pass where I modeled the architecture of the Ruby server into Go, I was at 500-some thousand messages a second. The current performance of it is about 5 to 6 million messages a second on this machine, this little MacBook Air, which I'll show you in a second. I think I can get it to about 8 in my copious free time, which does not exist. But I have all the stuff that I know what I can do. And Go's helped out a lot too. It's really matured from 1.3 to 1.4, and then looking at 1.5. So this is courtesy of Brave New Geek, where Tyler Treat, I believe, did a dissecting of message queues, and he ran the test, and he immediately sent me an email, and he says, it must be broken. You know, this isn't right. And so we talked back and forth, and he was really surprised at how fast it would go. And what I'm going to show you in a second is that this right now is one of the worst performing tests you could run on NATS. And I know that, and I have stuff that I'm going to try to actually make a lot faster. But if you look at like Ruby NATS was, you know, it was running probably about 700 or 70-some thousand a second. You see all the other ones, and again, the link is right there to the full article. But we do about 2 million or so per second. And the receiver throughput is actually the same, where sometimes things become massively imbalanced, right? The publishers overrun the subscribers. So if I can give a demo, let's see if this works. Okay, so this, I don't know if you guys can see it. This is essentially just running a benchmark test within the GNATSD repo on this box. I don't know if how well it'll run, but we'll figure it out. So the first run, which again might be hard for you to see, it runs a publisher with no payload. So essentially, I'm just figuring out how much processing power the subject distributor and the framing and unframing event protocols are running inside of the server. And it takes about 186 nanoseconds per operation, %. So that's about 5-point-something million. I'd have to type it up in a math thing. As you can see, the big graph we had a second ago when it was a 4K payload, that's the worst, right? We're at 47,000, almost 48,000 nanoseconds per operation. Again, I know, or I have an idea of how to fix it, so I just have to get to it. So that's pretty fast for a MacBook Air, right? You know, you're cranking along pretty good, and I still think I can get it to about 8 million or so. We'll have to see. In terms of, this is actually out on a cluster on a DigitalOcean running, so I'm going to start up the server. That's how fast it starts. And then I'll run a benchmark. This is actually running the Go client, which is not very high performant yet. There's a lot of stuff I need to do there. But again, publishing speed is about 451 operations per second. Pub sub is about 1541, meaning I send something and I receive it back. And then publish speed via channel, that's a Go mechanism, is a little bit slower. Actually, it's a little bit faster, sorry. So I actually did a full-blown presentation for GopherCon, the very first one that was launched last year, on everything I did around optimizing the GNATS-D server. So I put the link in there if you guys want to check it out. It goes into massive, graphs, no flame graphs, like Brandon does. But kind of talks about how we actually squeezed from 500,000 a second to 5 or 6 million a second. So text-based. Everyone who likes high performance says you never do anything in text. I obviously disagree these days. It's easy to get started with new clients. It really doesn't affect performance. And you can tell that directly to a server. And it's amazing how approachable things are. And I watched Salvatore, the guy that wrote Redis, do that for a client. They're like, well, what language do you support for the clients? And he's like, oh, watch this. And he just did it. And so now, if you guys want, if you have it out there, and I'll do it for us, we can just telnet to demo.nats.io on port 4222. And let's see. Can you see that okay? There we go. Make it a little bit bigger. So what's interesting there is that the very first thing I did was I hit enter, which was a protocol error, so it immediately chopped me off. Remember, it protects itself at all costs. But if we go in, I can do things like sub foo1. What that means is I want to subscribe to foo, and I give a closure. Closure just means that the connection that it's talking to, it understands what 1 means. And whenever you match on something, send that message back to me and reference it as 1. It could be anything. It doesn't matter. It's just a closure for each connection. And it says, OK, no problem. Now I can do pub to foo2, meaning how long the payload is. This is kind of like HTTP, so enter, OK, and enter. And so what happened was it published a foo, it said OK, and all of a sudden there's a message foo1, remember, is the closure, the subscription identifier, and 2, which is the size of the payload. So now what I did was I said, actually didn't, I'm going to do it again because you couldn't see it. Sub foo bar 3. So that means subscribe to foo, join a bar group, right, which is now already another member in there, and the subscription identifier, again, it says a closure, I'm just incrementing these, is 3. So now when I pub to foo to, actually let's do this, 11, hello world. You see that we got 2 messages. One was for 1, one was for 2. If I do this again, that bar group is we're figuring out which one of those. There's only going to be one of them that gets it. Pub foo 2. Okay. So now all of a sudden they got only 1. Oh, I know what I did. I actually did the auto-pruning stuff, which I'm going to show you guys in a second. So how do you actually monitor these servers? The monitoring is based on HTTP. It's modeled off of something that when I was at Google, everything inside of Google has a VARZ endpoint. Now you can only get to it from the inside, so you can't hit it from the outside world. And they already had key value pairs, and we actually do JSON payloads. And so you can actually, again, curl against demo.nats.io. And I'm actually going to start this process, which will actually is a NATS top version. So it's actually watching for people who actually connect to this thing. So if I do this again, you'll see that it now has a connection and it can watch it. But on this one, if I say curl against demo.nats.io 822, which is the monitoring port on VARZ, again, might be a little bit hard to see, but essentially returns an option structure around the max connections, the ping interval, which is a way to make sure TCP/IP doesn't go dead on us, all different types of things. And it says how much memory it's using, how many cores it's using, the CPU, number of connections, routes, remotes, in messages, out messages, and all stuff. Now you can also do conz, which if one's connected to it will return 0. But if someone starts connecting to it, you actually see detailed information about each connection on there as well. So in terms of the clients, again, we have a Go client, Node.js, Java, SCaLE, Ruby, Python. We're going to be adding probably Lua and C and C++. Inside of Apsera, we actually have a C++ that's built directly into Nginx. So we actually can update Nginx routing tables on the fly at, ours are digitally signed and encrypted, which is the most it costs to unwrap them, but about 400,000 to 500,000 times a second. So as things are moving around and you're trying to route to figure out where it is, that's kind of how we actually achieve that. So we talked about the fact that it's clustered. It's full mesh one hop, meaning all of these servers are connected to one another. Now, that doesn't mean that they both have to know about each other, but there has to be a physical link in between them. And the reason that it doesn't have to require bidirectional is there could be a NATing process in between the two. So I might be able to reach you, but you can't reach back to me. But once the connection's established, it's bidirectional. And so, of course, the client connections are going to connect to one of the servers. And by default, unless you tell it otherwise, across all the clients, they randomly pick a server out of the server pool. So we just spun up 1,000, of these clients. They would randomly kind of distribute themselves across the server set. And of course, if this thing goes away, it immediately reconnects. The reconnect speed is usually about 10, 15 milliseconds or so. As long as we can see the chop, if that makes sense. Hopefully it makes sense to each other. So when a socket goes away, sometimes you know, sometimes you don't. And so when we looked at the monitoring thing and you saw ping interval, the reason that there's a ping interval is because if we don't know it went away, which in cloud platforms a lot of times that happens, anybody who's running AWS probably has experienced that, where the machine just goes away, but nobody that's connected to the socket thinks they did. That mechanism actually allows it to go away. And it can be initiated by the clients or the servers. The servers both do them. So the auto-pruning part that we talked about earlier. Again, this is a big deal to me because of the patterns that we use quite a bit. Why? Well, again, if you're asking a request reply where you want one answer, but of a very large N, again, think Google, this does not work well at all on any of the existing messaging platforms that I know of. And so you're able to express a limited interest a priori. The system actually used across clustering as well circuit breakers. And I actually can show you in the Telnet session what this looks like. But essentially I can say subscribe to foo, and I can say unsubscribe to foo after one message, 2 messages, 10 messages. And so that state is actually propagated throughout the cluster, but you're still receiving messages, right? It's just formed a circuit breaker. But once you actually hit whatever that max is, it trips all the way across the cluster. And so your client library, actually, let's say you're sending out to 10,000 people and they're blitzing back as fast as they possibly can, and you just want one answer. Your client library might see 6, 7, maybe. Right? And that's easy for them to throw away. So it delivers the first one, it throws the rest of them away. Most messaging platforms, you'll have to throw away all 10,000 on the client that actually did the request. And so again, I don't know if anyone's seen these graphs, but you see these massive CPU spikes going along. It's easily accessible in protocols, which I'll show you in just a second. And all the clients that we support it. It's on by default in request reply. So remember, request reply is making no assumptions about who you're asking. Right? So I could be simply sending it to foo, and foo could just be all of you, and you're all going to try to respond. It could be that I'm sending to foo, but you all are part of a group called SCaLE X, or SCaLE 13X, meaning only one of you is going to respond, and the system will do that. Or it could be a combination of both, but makes no assumptions on that. Actually, before I do that, I'll try to show you what I'm talking about. So when I telnet, I'm going to subscribe to foo. Oh, see, I didn't type it in right. I had to put the closure for the. Hold on. Subscribe to foo. Subscription ID 1. Pub to foo. 2. Send OK. I get it back. Now I'm going to do. Is it usub or unsub? We'll find out really quick because it'll yell at me. Unsub 1, which is that subscription ID, after I receive one message. And if I typed it wrong, it will kick me out. Oh, I got it right. So now, what the system actually did was it set up a circuit breaker inside of the system. So I'm still active. The interest graph, hopefully people get what I mean when I talk interest graph. So when I send a message, it's actually reverse-traversing the interest graph. The interest graph flows towards me, data flows in the reverse way towards the interest graph. So now when I do a pub foo to OK, I should get the message, hopefully. Actually, it didn't. Oh, it already has one. Sorry. I'll do that again. Sub foo to unsub to 1 pub foo to OK. Pub foo to OK. Nothing. Does that make sense? I know that kind of. So what happens is the circuit breaker and the subscription state is always known. And so what I mean by that is when I did the first sub and I sent the message to it, the system knew that it already received the message. So when I said unsub after 1, it said, well, that's actually instantaneous. But the second pass through, if you notice, the first message got delivered, the second one didn't. Again, very low level. Most people probably could care less. At very, very large scale with that pattern of request reply where you don't know the audience, you care a lot, or at least we care a lot. So in terms of the summary, NATS is modeled to be an always-on dial tone. It was inspired a little bit by how we think kind of the brain works. It doesn't do all of these things that these enterprise messaging systems do, right? It just actually reacts. And hopefully those in the audience can understand the notion of like idempotent state transitions or compensating transactional models. So idempotent means I can keep sending it as many times as I want, and the state transition is always consistent on the other side. NATS works great for that. Right, and so in Cloud Foundry's original architecture and definitely in Continuum's architecture, we use pub sub, we use distributed queuing, we use that request reply of large N pattern, and the system is actually always kind of doing the right thing there. It's high performance. I can make it faster, but it does pretty good itself. It's clustered servers, and the clients are cluster aware without any additional external support from DNS or anything like that. And clients are in many languages, but I'd love to see more people contribute. Again, NATS is not going to be for everyone, and I'm okay with that. Some of the futures, again, there is inside of Apsara direct C++ in the Nginx evented model, meaning it's directly plugged in at high speed, and we're probably going to OSS that. We're pulling apart that low-level stuff and then our identity and digital signatures and encryption pieces. There's a lot of performance gains I can still do in the server and the clients, which I'm hopefully get a little bit of spare time to work on. We'll probably see a C++ client. I will probably model the C client after the high Redis clients that can use multiple eventing libraries like libuv and libev and things like that. And Lua clients. A lot of people like Lua. It's very, very fast, very, very straightforward. I actually like it as well. Monitoring dashboards, so instead of that NATS top, you actually can kind of see something fancier there if you want. And then an auto configuration service. So if you're actually trying to set up a full mesh one hop, it's tedious, right? It would be really kind of nice to say, hey, here's a new server, and I have an API token. I want you to join the group that's represented by this API token. It automatically gets its config, starts up, and it does everything for you. You don't have to worry about any of that. And so those kind of some of the things that we're thinking about going forward. Thank you. Again, it's twice as big as I thought the number of people who would show out, and it's a very low-level kind of a grungy topic, but it's one that's near and dear to my heart. Here's some additional resources. NATS can be found at nats.io. Here's the high-performance Go server. Oh, sorry, this is a Docker image. Yeah, there's a self-contained, no operating system. It's 6 meg big Docker image that I built, which was interesting. I was trying to impress upon myself and others that Docker, it utilizes the kernel underneath, so you don't actually have to put a lot of stuff around it if you don't want to. And Go builds nearly completely static binaries, but if you trick it, you can. And so it's kind of interesting. If you go to GNATSD and look at kind of what we do to build this, it's kind of interesting. So I build it in terms of a larger OS inside of Docker. It downloads, GNATSD, compiles it, and then it trampolines again into itself into Docker on a scratch image, which nothing's there, and copies just the absolute static executable onto there. So that's the only thing that's in there. That's kind of a neat trick, I thought. And then the last link is just the really in the weeds descriptions of what we did to make the Go server, the GNATSD server, very, very high performance. So, questions?
I got a question. So, your first use case was Cloud Foundry, right?
So the question, paraphrased down, is it was originally kind of designed and architected for Cloud Foundry. Where do you see its applicability in future PaaSes or in other types of cloud or distributed platforms? The notion of NATS was a collection of ideas that I had before I built it for Cloud Foundry. So yes, that was kind of what forced me into actually writing the code. But the ideas have been percolating in my head for quite some time. Again, I built it for myself. I didn't expect anyone to care about using it. But if you look at the notion of applications that are using enterprise messaging systems, that's probably not the use case that you want. However, the importance in distributed systems of a control plane. So OpenStack has one, Cloud Foundry has one, Continuum, AppService Continuum has one. Lots of things have one. Amazon had one that famously wasn't working great when they first started out, and they've really done a lot of work there. That's probably its sweet spot. Now, that being said, if you're culturally building cloud applications like, the 12-factor and all this other stuff, it might be applicable there, right? Because you're not making a lot of assumptions about what the messaging system can do. But it was originally built as a always-on, very high-performant, always accessible control plane mechanism for kind of modern distributed applications where we used idempotent state transitions and compensating transactional models to actually modify, the distributed state. Yes?
How do you monitor performance in a production environment, both total throughput and percentage delivery?
Yeah, so the question is, how do you monitor the system in production? And in the presentation, we talked about that every single server has that var z endpoint on it that you can pull all of the statistics in real time from it, and they can easily be aggregated. And of course, inside of Apcera, we have aggregation and fancier things. In the open source GNATS-D that we have there, those endpoints are there both for what we call var z, and then there's detailed information for every single connection. So you can actually pull var z and say, hey, there's a spike, in traffic all of a sudden. You can look at conz, and it'll say, you guys are all okay. It's you know what I mean, that's doing it. There's a massive spike, and you can look at it that way. Yes?
What about SSL wrapping into this? How do you handle that?
Yeah, so the question is what about SSL wrapping? So the Ruby server, which still exists, I wouldn't recommend using it, but it does exist, had TLS baked into it. But it was kind of broken, so it kind of gave you a false sense of security because of the way it dismissed certs and cert attribution. Go, when we wrote the Go server, again, the work was prompted inside of Apcera, which was built on day one that every single message state transition, regardless of the plumbing, was going to be digitally signed and secured. So within Apcera's continuum model, everything is not symmetrically encrypted. It actually is encrypted both on a class and instance basis of all the different actors within our system, meaning we can go over HTTP, NATS, we can stick it in a file, nobody cares. So for that reason, it doesn't do TLS yet, but part of the futures, I should have put that in there, it's on there. And Go now supports very high and strict cert chaining and cert checking on the TLS. So it's a need to do it, but within Apcera and within Continuum, we kind of solve that problem in a different way. So it's, to paraphrase it very easily, it's whether or not, you have to use the red phone, or you can use any phone, and actually you have your own device which will, make sure that no one can understand what you're saying. Yes?
Yes, rendezvous message, when you broadcast the message, do you consider the size of the message reaching down to the message?
So I believe the question was, within Rendezvous, did we broadcast messages out and do things differently on the size of the message? Is that correct? Yeah. So I left, TIBCO in 2003, so I have no clue what they do now. I can talk about how the reliable data program protocol worked before, which was we would have an MTU, so you have to bucket, chop things up. It was a NAC-based retransmission protocol, right? So you want to make sure you didn't have NAC implosion, and you had to essentially optimize for the number of times a packet was on the wire in case of a loss. Very, very boring, but actually kind of really interesting. When I first started writing the code for it, we had a single piece of, looks like, cable that you get from Xfinity or whatever now. That was the network. And so the loss patterns at that point on UDP was the FIFO buffers in your Ethernet card. So it was a random Gaussian distribution. Again, I'm experienced, I'm old. But as we started going to hubs and then switches and then routers, you started seeing these loss patterns where everybody over here except maybe one or two people got it, but that whole side of the room didn't get it. because, right, the switch would blow the back end port, right? It would just say, I give up, and it would blow everybody out. And so when we rewrote it, we were trying to optimize around an algorithm I designed called Am I Being Helped? Because when you miss something, you always have to ask for help. I don't know if that makes sense. But if I'm sending it and you're like, you get 1, 2, 3, 4, 10, you're like, crap, I just missed 5 through 9, you always have to ask. But similar to the distributed scheduling algorithm mechanism I told, where I tanked it and I would back off, this whole side of the room would randomly pick a number where they were going to ask. And they wouldn't ask if they saw that they were being helped. So the first person that would ask, I have to respond to them, but everybody else would see that they're being helped. And it was kind of an interesting thing there. Yes?
If I understand correctly, NATS consumes text-based messaging primitives. Can you send something like RDS through it?
Yeah, so the question is it text-based where it's actually limiting? So the answer is that the payload, which if you remember when I said like pub foo 2 essentially signaled the system there's 2 bytes that are coming after this. They can be anything they want. So the NAT system looks for exactly 2 bytes. It doesn't look for /r/n or anything there. So once it hits that, it's in binary mode, if that makes sense.
So you have to know the size of the triple that you are going to send through. You have to know the size of the message prior to sending.
So the question is, do you need to know the size of the message? At a protocol level, yes. All the clients, though, you don't need to, right? The clients will figure that out. So, for example, in the Go client, the base level API, you hand it a byte slice, which is a fancy word for a dynamic array in Go. But there's upper level constructs, even in the Go client, where you can hand it a structure, an internal structure, and tell it that you want it encoded in JSON, and it handles everything. So it encodes it in JSON, knows how big it is, and then sends it that way. But from the little telnet example we did, yeah, you need to know how big it is.
So is it only the size? There's no introspection in the pattern inside the message?
So the question is once I am given the size, is there any introspection? And the answer is no. I don't look inside of the payload whatsoever. Yes?
In the request response model, is there any optimization on the second line? The first line is responded. As the second line, can it be truncated processing in any way or anything like that one?
So the question is, in the request reply with large N, is there any optimizations for the clients who are number 2, let's say, to respond? The answer to that is no. The reason being is that a personal preference of mine, you want to be very cognizant of what I call positive chatter on a control plane. So again, remember the distributed scheduling algorithm, if you can't help me, I don't want you to say a word. Don't tell me you can't help me. That's actually bad. If you wanted to do a mechanism where the client itself could actually detect that it shouldn't actually try to send, it would actually have to distributedly or a priori figure out a subject that we're all going to listen to see if someone else has responded to. And so the control traffic pattern, especially on large N, goes up like this unnecessarily. So for example, like a MacBook Air, one client can send 6 million messages a second. As long as that thing's fairly close, let's say in the same rack or whatever, it's actually better for it to just send it, and then the server trunks it. It knows that it doesn't need it, and it throws it away immediately. So it's very cheap that way. And actually it's counterintuitive, but it would actually be way more work for each client if they were trying to do it than just sending the bytes anyway. You could do it, by the way. It's a pattern you could implement. I would just be careful of what I call, positive exponential growth, or what's called a, positive chatter on a control plane.
Do you plan adding support to multi-part messages?
So I think the question was, do you plan on adding support for multi-part messages? That's actually a great question, because I don't know if anyone picked up on it, but when I queried the one server, it had a max payload size, which is configurable by you, but I would highly suggest you don't make it very big, because if it's big, you can do a denial of service based on a memory footprint of a server. And so you would actually need that. I think the system we were running here could take up to 10 meg messages. But we don't have any support yet, but it's trivial to do. But it would be better, I guess, if the clients did it, for you. Right now, the clients, when they connect to a server, if you remember when I actually telnetted in, I get this blob, JSON blob that kept flying at me. That's the server kind of indicating to the client everything it can do. So the clients know the server can only support up to 10 meg. So if you try to send something that's 10 meg plus a byte, it'll error immediately. It won't actually try to send it. Any others? Perfect. Thank you. I appreciate it. Oh, yeah. You come on.